Okay, so in this example, we're going to do an empirical formula, but we have a different process. This is called a combustion analysis. This is when you take a compound, you burn it, react it with oxygen gas, collect the products, and use those products to help analyze what the components of the compound were that were being burned. In this case, we have an unknown hydrocarbon with carbon, hydrogen, and oxygen as part of the formula. It's reacting with oxygen gas to produce carbon dioxide and water, and we have the values given there. Now, the process for this is the same. We are going to find an empirical formula by finding how many moles of each element from that compound there are. The problem is that we could easily enough find the moles of carbon and the moles of hydrogen using our stoichiometry and what we have from these formulas. The issue is the oxygen. Oxygen is in every one of these compounds or element, and we don't know exactly how much oxygen is in this formula because all of the oxygens here are from both of these combined. So we don't have a way of distinguishing the oxygen that came from just this, but we have a workaround. So the first thing we're going to do is we're going to find the moles of carbon and the moles of hydrogen using these values. So we're going to start off with our carbon dioxide, 16.80 grams of carbon dioxide. We're going to convert that into moles, 44.01 grams carbon dioxide, 1 mole. One mole of carbon dioxide is 1 mole of carbon. We're going to do the same thing with the water. We're going to take our 10.32 grams of water. 1 mole of water is 18.02 grams. 2 moles of hydrogen to 1 mole of water. Remember, we're doing this because when we're dealing with empirical formulas, we deal with the single element or atom of the elements and not the actual molecule. So hydrogen, nitrogen, oxygen, all of those elements that are diatomic, we would use just the single atom when we're doing these. Here's where we have to do something different. We have our moles of carbon, we have our moles of hydrogen. We need moles of oxygen. To be able to find that, we need to find out how many moles of oxygen are in this compound alone. Our key is that we know that this 11.85 grams is equal to the masses of carbon, hydrogen, and oxygen in that compound alone. So if we treat this as kind of an equation where we got carbon, hydrogen, and oxygen equals the mass of carbon plus the mass of hydrogen plus the mass of oxygen. If we know all of these values, we could find our oxygen mass. All we need to do is convert these moles of hydrogen and carbon to grams to be able to plug into this equation. So we're going to take that extra step. sorry, I didn't take that out quite far enough. Now, since we know that this mass is 11.85, we know the mass now of carbon was 4.584. We know the mass of hydrogen was 1.156. Oxygen mass is going to equal 6.109, actually going to be 6.11 grams of oxygen. I'm not going to go into details of the why, but it has to deal with the significant digits and addition and subtraction. We do that so few times, I'm not going to worry about it. So all we need to do now is take that 6.11 grams, convert it to moles. Now we have our moles of carbon, our moles of hydrogen, and our moles of oxygen. We divide by the smallest. In this case, it looks like it's going to be 0.3817, almost a tie with the 0.382. So our formula is going to be CH3O. Now that's the empirical formula. In the OWLs, not only are you asked for the empirical formula, but you are also asked for the molecular formula. And this can be done with this combustion analysis or any other problem. Once you know what the empirical formula is, if you know what the molecular formula's mass is, or the molar mass, or the formula mass, however you want to say it, if you know the grams per mole for the actual compound, then you can set up a proportionality between the masses of these two to determine what the molecular formula is. So I'm going to erase to make some room. And the basic idea is to take the molecular formula's mass divided by the empirical formula's mass, and that's going to give you your proportionality. So in this case, we're going to have 62.07 divided by 12, 15, 31, rounding it in my head because it's close enough, and that's going to give me a value of 2. And what that means then is that this empirical formula is 2 times less than what the molecular formula's form is. So we would simply say CH3 H3O would need to be multiplied by 2 times. This then means that the molecular formula is going to be C2H6O2.